All right. Here we have a consideration for, instead of a really thin line of charge, I'm going to do a consideration for a electric field outside of a uniform stick of charge. Now, by calling it a stick of charge, I'm going to be thinking of it as being a very long stick. So it's more so like you're in this region looking at it. So much so that this is seemingly infinitely long. So there's my shape. What's the electric field coming out of this thing? I'm going to disregard the top and the bottom. I'm going to just be looking at the electric field coming out of the sides. I'm going to say that it's so long of a stick that the ends are irrelevant. Now, if this was a really short thing, then I wouldn't be able to make that statement. But here, I'm making that statement. The Gaussian surface outside of a uniform stick of charge. There's my Gaussian surface. It's surrounding the charge that I'm concerned about. Okay, and repeating the symmetry of that situation. Note that no electric field is pointing through this surface at all, and no electric field is pointing through this surface at all. It's only pointing through the sides. That side length is, I'm going to zoom in a little bit, is L. The radius of the actual shape of the stick, the cylinder, is R, and the radius of the Gaussian surface is little r. Okay. What is the area of my Gaussian surface? Note that I'm only doing the area of the sides, not the top and the bottom. And just like I did in the thin line of charge, the area of that Gaussian surface is going to be length multiplied by 2 pi little r. Done. Q enclosed by it. Well, that's going to be all this. This is a uniform stick of charge, so we're dealing with a charge density, which is charge per unit volume. So Q enclosed will be equal to the charge density multiplied by the volume of the charge there. Okay, the volume is the volume of a cylinder, and that cylinder has a volume of length multiplied by pi capital R squared. Okay. In the same way as the area of the Gaussian surface was L multiplied by the circumference, the volume is L multiplied by the area. Q enclosed. Let's put these things together and we'll get ourselves a electric field. Electric field multiplied by the area of the Gaussian surface is equal to Q enclosed divided by epsilon naught. That'll be the electric field is the area of the Gaussian surface, L 2 pi r. Q enclosed, rho L pi capital R squared. Don't forget that epsilon naught. Boom. A little bit of cancellations. Pi's cancel. L's cancel. Nothing else cancels. Get the electric field is equal to rho capital R squared divided by 2 epsilon naught lowercase r. Note that for the stick equation, we also had this one, not the stick, for the line of charge example, we had this 1 over r relationship as well. So outside of either a stick or a line or just a big tube of charge, we're expecting this 1 over r relationship that points outwards. Or you could have said r hat, either way. That half is done. Now, why is this only half of it? Because so far we've only looked at the outside. Since this is a uniform stick of charge, there's electric field inside of that stick as well. Let's consider inside as well. Okay. Inside of that stick, the stick has a radius of capital R and a length of L. I'm just going to use the L on the Gaussian surface. I'm going to consider the electric field, like so. Same outwards idea as previous. In actuality, there will be some turning at the edge here. So I'm going to be focused not on the outer edges, I'll be focusing on the inner area. Which is why when I draw the Gaussian surface, I'm only going to be drawing it in this region. Which only goes out to radius r, and the whole thing has a length of L. What's the area of that Gaussian surface? Same equation as previous, actually. L pi, 2 pi, little r. What's the Q enclosed? The charge enclosed by that Gaussian surface is going to be rho multiplied by the volume of that Gaussian surface, because it's only going out to this boundary. So that's going to be L multiplied by pi little r squared, which is the volume of the Gaussian surface. This is why I don't say it's the charge of the Gaussian surface, it's enclosed, because in this case, it's only out to the Gaussian surface, whereas in the previous example, the charge only goes to the edge of the object. That's why I use this term enclosed instead of Gaussian surface. It's enclosed by the Gaussian surface. Electric field inside times the area of the Gaussian surface is equal to charge enclosed divided by permittivity. L 2 pi little r rho L pi little r again squared though epsilon naught. L's cancel. Pi's cancel. 1 order of r cancels. And we're left with the electric field is equal to rho r over 2 epsilon naught. Outwards is the electric field inside of a rod of charge. Last thing I'm going to do is I'm going to combine these two results. We got our outside, we got our inside. So to draw this out, we've got the electric field magnitude, we've got inside, we've got outside of R. So variable is lowercase r. The actual size of the object is r. Inside, we have this neat linear relationship that goes all the way to rho capital R over 2 epsilon naught. Outside, it also goes to the same rho R over 2 epsilon naught. If you plug in R is equal to capital R, then one order of R cancels, and you end up with this exact same thing. Except for outside, you have a 1 over R relationship. Okay, and there we have it, the electric field inside and outside of a stick of charge. Done and done.